Hi, welcome to today's video. Today I'll be talking about figuring out and finding out the electric field due to a uniformly charged wire infinite in length using Gauss law. A lot of students have problems with this, so I will be explaining this in depth and completely. I'm Atray and I teach at Cosmic Essence Education. Do subscribe this video, like and subscribe our channel so that we know that you are enjoying our content. So first things first, we'll be discussing what Gauss law is very quickly so that you understand how we'll be using this today. Gauss law is simply, it simply says that the flux passing through a given area, that is flux passing through a given area, is equals to the charge enclosed by that area upon epsilon. This is what Gauss law is. I'm not going into the details of Gauss law right now. I just want to discuss what this is. So that means when I put it down, this is E dot S. S is the area, E is the electric field, which is equals to charge enclosed. Let's call that Q upon epsilon. Epsilon is a constant. So this is the Gauss law formula, and we'll be using this and utilizing this to figure out the electric field through a uniform wire, uniformly charged wire. So we're talking about a uniformly charged wire. Why are we talking about a uniformly charged wire? Is because if it's not uniform, then it will be very difficult for us to figure out what is the charge that each part of the wire has. So it becomes exponentially difficult for us to figure out the electric field by that wire. But if it is uniformly charged, what happens now is when I make a wire, or when I think of a wire, I can imagine the charges being at the same equal distance from each other and spread out evenly throughout the length of the wire. Okay, so I can imagine that throughout the length of the wire. Through that, once we figure that out, I call that linear charge density. Linear charge density, which I am denoting by lambda. Linear charge density is nothing but the amount of charge through that wire per unit length. Now that unit of length can be anything. It can be per meter, it can be per centimeter, it can be per millimeter, depending on what I am looking at. But the idea is, if the wire is uniformly charged, that means the charges are easily and equally distributed along the wire. I can then figure out that what a unit part of this wire will have the charge, what amount of charge a unit of this wire will have. We are calling that linear charge density. Very important to understand, because this comes up again and again as we move along with different other objects like this. Now, a very important part in this is to understand that when I look at this wire, suppose I am taking this small section right here in the middle, and if I imagine the electric field created by this section, obviously I can see that because this becomes this almost becomes like a point charge, right? If I forget everything else from the wire and I only think of this part of the wire, it becomes like a point charge. That means throughout its radius, sorry, my circle is really bad, I'll try to make it again, but throughout its radius, the electric field by this charge will be the same. That means the electric field by this charge over here and over here and over here will be equal, because it becomes the center of this circle, right? And the electric field will be radially outwards. Radially outwards. Like this. A very important thing. Okay. Why are we discussing this? Because this will allow us to figure out which form of Gaussian surface are we supposed to take. Okay. Now this is the first thing. That is, for a component, a piece of a part of the component of the wire, it creates an radially outwards electric field in its own plane. Okay, we are talking about in its own plane, not below, not above. Now let's now imagine these two parts. They are equidistant from this point, or let me take it a little bit up so that you can sense that they are equidistant. Both of them are equidistant from this point, and what happens now is, if I take the effect of these two at a certain point on this radial circle in the plane of this charge, what's going to happen is, this part is going to push it this way and this part is going to push it this way, right? Both of them are at the same distance. That means this is equally the distance from of this point from both of these parts is equal, and so the force applied by both of these parts and sections is equal at this point. Now, as you can clearly see, if the forces are equal, the vertical components will cancel each other out, right? Because the magnitude is equal and obviously the angle is equal. Therefore, the only remaining possible option is of a radially outwards force. Radially outwards force. So the pieces, the effect of force of parts of wire, both above and below, they kind of add up and only give us a radial electric field as well. Very important to understand, right? So once we have that understanding that, hey, everything, the piece in the center, that means the charge in the center, is also creating a radially outwards electric field, as well as the pieces or the charges above and below this charge are also giving us a radially outwards electric field, right? Now I can take a Gaussian surface which encapsulates all of this, and the Gaussian surface perfect for this is a cylinder, right? So I take a cylinder, I'll try to make it equal to this. I take a cylinder as my Gaussian surface. Now, what is a Gaussian surface? Gaussian surface is essentially an imaginary surface that I can take, depending on the situation, to figure out how much flux is passing through this Gaussian surface, and if that is the flux passing out that Gaussian surface, how much charge is encapsulated in it, and I can then use Gauss law to figure out the electric field. So now, as I take my Gaussian surface as a cylinder, I can clearly see that the top surface and the bottom surface will have no flux passing through it. Why? Because all the electric field is outwards and radially outwards. That means it is perpendicular to these surfaces, right? So the electric field or the flux passing through both of these surfaces is 0. Okay, so the flux will be 0 plus 0, 0, 0 is for the top bottom surfaces, plus the flux of the cylinder, right? Now, how much will this be? Flux is equals to electric field into the area. What is the area of this? 2 pi r L. L is the length of this wire encaptured in this. So cylinder is equals to electric field. This is exactly what I want to find, and area is 2 pi r L. L is the distance or the length that I am taking for this cylinder. L is that distance. So I have this. Therefore, this becomes my flux. As soon as I get my flux, I can equate it. I can equate my flux with my Q upon epsilon. What is Q here? Q is the linear charge density, which is charge per unit length, into L, because L is the length of the wire encapsulated in this cylinder. So lambda into L upon epsilon naught. Therefore, I get my electric field as lambda upon 2 pi r epsilon naught, and that gives me the electric field by a uniformly charged wire through Gauss law. Now the important thing over here is this is only applicable, and this value is only true for an infinitely long wire, right? Because if the wire is short, the ends will start interfering, and we will have to take that as an edge case and understand that as separately. But right now we are only talking about an infinitely long wire. But sometimes for a very long wire, we can also take a small part in the middle, and the this result comes out correctly for that as well. Okay, so that is what the result is all about. At the same time, the obvious assumption over here is that the charge is uniform on that wire, right? So that is an obvious assumption that we have to take care of and understand, right? So that is it for today. I will talk to you in the next video. Thank you for watching that video. I hope you liked this video, and if you did, please do like, subscribe and share the video with your friends as well as your family and cousins, so that you can have a better discussion with them and start thinking about the subjects that we are sharing with you. In the next video, we will be talking more about applications, as well as if you want me to cover a specific topic, please do put it down in the comments below so that I can discuss it, and I will be able to put up new videos soon for those topics.